My name is Robert Llewellyn, and each week I give someone interesting, fascinating, wonderful, clever, funny, beautiful a lift in my car. Now, this week's passenger is just terrifyingly clever. He is Professor Brian Cox. I know very little about Brian. I know that he works at CERN, where there's that big donut thing that they fire little particles around in to try and work out if they can develop nuclear fusion, or fission. I hope he'll explain which one is which. And I know he's just written a book, which is called Why Does E Equal MC Squared, which is a bloody good question, because I've never really known why. And I'm just going to try and see how far I can follow him, because I've got a feeling that with my grasp of physics, fairly limited, he's going to leave me standing quite early on in the conversation. But he's a charming man and very funny, and he used to be in a pop group that I've heard of. So let him explain. Please welcome to the passenger seat, Professor Brian Cox.
I've done snorkeling, so
Right.
at least I know that what the feeling's like to get that vertigo kind of feeling when
Yes.
you're looking down and it's really,
Yes.
you know, and I did feel a bit weird when I did that. But we've got it's in Hawaii, so I can't miss it really. This
Wow.
is, you know, do you mind?
Do you mind going to Hawaii and doing some
diving
diving?
in Hawaii? You know, like- So I think they just want to film me just falling off a boat and then floating around underwater.
Yeah.
And well, it's actually about.
Yeah, because what's it actually? I'm trying to work out what it's about.
It's a way of talking about the atmosphere of Jupiter, believe it or not.
Wow.
So we're gonna do a whole sequence where, and I'm not gonna do the first bit. They've got footage of the highest parachute jump, so which is essentially on the edge of space.
Yeah.
And so we're gonna follow the sort of increase in density and pressure as you come down from the highest parachute jump down, and then go into the ocean and go down. And so we're gonna try and talk about pressure, what it does to gases and turns them into fluids, and it's just a very visual way of doing that.
Right.
So I'm going to do the last bit.
I see. And is the atmosphere of Jupiter denser than ours?
Oh, well, yeah, immensely. In
Right.
the core, it ends up being metallic hydrogen in the core. It's so dense and such high pressure that you've got this liquid hydrogen that essentially behaves like a metal in the middle.
And do you mean in the centre of the planet?
Yeah, but it's all gaseous. I mean, there may be a rocky core, but it's, you know, 99% of the thing is gas, but then it becomes liquid because it gets so pressurized. So it's a huge thing. So,
someone did say that the first thing you'd say, the first thing I'll say when you start talking is "Wow." And they were right. I'm really not, because I never knew that. I thought all planets were like lumps of rock with no atmosphere.
Especially a star. I mean, it's pretty much like the sun, except it's not big enough to initiate fusion.
Wow.
But it's just hydrogen, helium. There's nothing else in Jupiter, pretty much. It's a big ball of gas.
Wow.
But
it looks like a planet though when you see a picture
it's solid.
of it.
It reflects. Well, it's solid in the sense it reflects light,
right.
but it's gaseous, liquid, and
Wow.
metallic hydrogen. It's like the sun. I mean, the sun's got no solid core, as it were. It's just a fusion reactor in the middle. So any bigger, and it would be like that.
Wow, because this is, I mean, that's the big questions that everyone, you know, that you don't have to look at all the questions, but there's a hell of a lot of them, but they're all about that, you know, about CERN and about what the experiment that happened recently, and all that stuff is clearly, and I mean, I haven't got the first idea, or I'm assuming, let me assume it, then you put me right, I'm assuming that scientifically there's the potential to recreate what happens in the sun within a controlled environment on Earth.
That's easy. I mean, that's a fusion reactor.
I see. That's easy.
I just made a documentary on those things actually, so I know about those as well. That's the easy. We did that in nuclear bomb explosions. You don't
that's effectively all that is. That's what that is. Right. Oh,
yeah.
right.
Fusion bomb. A fusion bomb is a little star.
Right.
So that's 1940s.
Oh God, that's old.
50s technology.
It's rubbish.
So
then what's the next step then? Because that shows my level of ignorance is fairly impressive.
Well, CERN, we're recreating the conditions that were present less than a billionth of a second after the universe began, which is astonishingly hot.
Right. I mean, so really hotter than.
It's a billionth of a second after the Big Bang. I mean, so nuclear explosion is, let's say, a minute after the Big Bang or something, which is a long time.
Right.
I mean, that 15 million degrees, the temperature in the centre of the sun, that's a doddle.
What's happening at CERN then? Because is that where are you effectively working there, or you do work there occasionally? I don't quite know what you're.
So my academic involvement is on Atlas, which is one of the two big experiments there. Well, there are 4 experiments there actually.
Right.
So when the machine starts working, which will hopefully be October,
Right.
then they start taking data.
So it still hasn't actually properly worked yet?
No.
Right. Because it went a bit squiddly, didn't it?
It did, yeah. Are you recording now, by the way? Is this
Yes.
part of the...
Yes, sorry. No, we've
I
started.
was chatting away.
No, absolutely.
Yeah, I mean, it works, which is so last September we turned it on.
Right.
And we got beams going around both ways around the machine,
Right.
which means it works.
Right.
Which is a big step,
Yeah.
because you never know that these things are going to work
Yeah.
quite until you turn them on. And then we had a problem with one join between two magnets,
Right.
which was essentially a manufacturing problem or
Right.
installation problem, but it was a join between two wires that carry about, what is it, about 13,000 amps.
Wow.
Is that right? At full power.
Right.
But they're like a piece of fuse wire. So the only reason
So it's not a big, thick, fat wire?
no, tiny
Wow.
wires. And the only reason they can work is because we cool them down
Right.
to minus 271 degrees,
Right.
which is colder than the universe at the moment. The universe has got to about, it's got to about a degree or so hotter than that as it's
Wow.
cooled down. It's in 13.7 billion years after the Big Bang. It's
Right.
got to about 2.7 degrees above absolute zero.
Right.
And we run at 1.9, so it's cooler than
Right.
space.
Cooler than space.
And at that temperature, there's no electrical resistance, so the wire can take all this huge current.
Right.
But if they heat up a bit or something goes wrong, then suddenly you've got 13,000 amps going through something the size of a bit of fuse
Yeah,
wire, and it doesn't last
it's
long.
probably not going to last that long.
So it sort of, a little spark happened, and one of our 20 odd ton magnets jumped about a foot to the left.
Wow.
And we squashed about another 50 of them. So we had to take them all out,
Yes.
and they've all been reconditioned and rebuilt. They've gone back in, and they probably will come back online in September,
Right.
October, and then start taking data
Yeah.
as soon as we can, hopefully before Christmas. So, and it's at that point because I'm more of a data person, I
Right.
analyse data, so the data will start coming in, and then I'll start
Right.
working again. There are thousands of particle accelerators. Most of them are in hospitals, actually. They're
Right.
used to make isotopes, chemotherapy,
Wow.
and those things. So that's how you make
Right.
radioactive substances for medical use.
Right.
Or medical imaging, X-ray machines, those things. So the smaller ones are usually used for what we call light sources now. So there's a big one at Rutherford Appleton called Diamond, and its job is to make really small wavelength light,
Right.
so you can take pictures of things or movies of things very quickly. So you can look at cells, you can look at biological processes in cells,
Right.
even beginning to be able to make movies of viruses entering into cells.
Wow.
And so
wow.
you use them for the light
Right.
that gets emitted when you
Yeah.
send electrons, let's say, around in a circle. But CERN, we don't care that it's a circle, really. In fact, it's annoying that it's a circle in a way. It'd be better if it was a straight line.
Wow.
Because we don't want to send any light. We don't want to radiate light off, because we
No.
lose energy.
Yes.
What we want to do is get these particles going as fast as you can,
Yeah.
and then smash them together.
Right.
And then there you make these temperatures.
Right.
Insane temperatures.
Right.
So you can observe the universe as it was,
Right.
a billionth of a second when
Wow.
it began. And that's because it's simpler. For no particular reason why it should be, but it turns out it is. As you go back in time and everything gets hotter and hotter, everything gets simpler.
Right.
So all this complexity you see in the world, things like you and me,
Yeah.
Toyota Priuses,
Yes.
they're properties of an old and cold universe. So they're
Right.
all this structure and mess
Yeah.
has crystallised out in a way.
Right.
So if you want to see the underlying simplicity, which is there,
Yeah.
may be surprising, may not be. It's not, but it certainly is true that it's very simple.
Yeah.
Then you go back and you photograph those conditions, basically. So
Right,
you observe
right.
the laws of physics as they were
Right
at
at the beginning. Right.
when they were
right.
simple.
Wow.
So it's the best way we found of doing physics, really, at that level. I mean, physics is just understanding the forces of nature and the building blocks of nature.
Yes.
And the way you do that is build things like CERN. So it's not because you want to find another particle or you want to just bang things together for a laugh.
Yeah.
Because
Yeah.
physics has gone that way.
Yes.
Right? It's a direct line from Newton and Maxwell understanding electricity and magnetism and understanding the nuclear forces.
Right.
We've been led to this point where we need something that's 27 kilometres in circumference and 600 metres below the ground and a 135 megawatt power consumption.
So has it got its own power station? Presumably
No, we use a French grid, so we're beautifully carbon neutral because it's all nuclear.
Right.
So that's fine. So the Green Party should applaud.
Yes, they should definitely.
Well.
And would nuclear fusion remove, say, some of the slightly ill-informed fears of nuclear waste? And I mean, does it?
Yep.
Right.
It's in principle completely clean. So you don't, nothing happens at all. There's no waste products at all, basically.
Right. Yeah.
Actually, at CERN, one of the things that's been looked at is using neutron beams. So if you find neutrons into something, then it changes it. It makes it radioactive. But it can also take things like plutonium that have hugely long half-lives that stick around for tens of thousands of years.
Sorry, I'm just going through a slightly orangey light.
And it can convert them into things that decay away very quickly.
Right.
So you can, if you want, take nuclear waste, fire neutron beams at it, and get rid of it.
Right.
If you feel like it.
Right.
It's just quite expensive.
Yeah.
So it's cheaper to bury it.
Yes.
But if you really don't want to bury it, then you can get rid of it if you want.
Right. Give me a brief step-by-step thing of how you got into it, because I mean you've obviously got a very passionate group of followers that, you know, I was amazed at the response on Twitter of how many, I mean the detailed knowledge of your life was quite mildly alarming. You presumably were, you know, quite bright at school, I would guess.
Yeah, I mean I was always into space, right? So all I knew, and I didn't know whether it was, I was born in '68, so I watched the Apollo moon landings apparently with my dad, and then the first thing I remember really is the Apollo Soyuz link up in '75.
Yes.
But for me, so there was Star Wars and Star Trek.
Course,
I didn't know the difference at all.
Yeah,
It was just that, want to do that.
Yeah.
Astronomy, space, whatever that was it. So I remember going to school at 11, and when you go to senior school, and you do physics for the first time, and I was just really, that's what I want to do. Brilliant, I'm going to do physics.
Right.
And to the point where I refused to do French because I thought it was a waste of time because it wasn't physics.
Yes.
And so I can't speak French even though I work in Geneva, which is stupid. So you realise that you just
It might have been mildly useful.
Took a break at 18 and decided to be a pop star for a while. But
that's right, because I didn't know about that. No, do tell me about that, because was it?
That was well. There's a band called Dare first, which came out of Thin Lizzy. The keyboard player from Thin Lizzy formed the band when Lizzy split up, and he just happened to live near me in Oldham. Bizarrely, it was, and so I was 18, and he formed the band and said, "Do you want to join the band?" And so I said, "Yeah." And so I did that for 4 years.
Oh, did you? Oh, right. See, not 6 weeks in the summer.
No,
it was a long time.
No, 4 years. Two albums with A&M Records. Brilliant. Recorded both of them in LA. Great, and I'd only been abroad once, I think. Right. And then suddenly
you're in LA.
To do this. Yeah,
cutting tracks.
Yeah, and then toured with Jimmy Page and Gary Moore.
And what was the name of the band then?
That was called Dare.
That was Dare, because what was D-Ream? Was that?
Well, yeah. So
that followed that.
Left Dare because we had a fight.
Yeah, you've got to do that.
And in Berlin, really great fist fight.
I know, really, actual punch.
Yeah, actual fight.
Wow!
And halfway through a tour, that's the end of the band. Came back, applied to Manchester University to go and do physics. Right. So I thought, well, I'll go back to doing that.
Yeah.
And then joined D-Ream accidentally because a friend of mine was doing sound for them before they had a deal. Right. It was just Pete Cunner, actually, a singer, just on his own, really. And my friend rang up and said, this is just shit. They're never going to go anywhere. I hate it. Do you want to do the sound for them? Because I just don't want to do it. So I started doing the sound in my summer holidays before I went to university. And then joined the band kind of accidentally. So I had another pop career, but I was at university.
Right. Oh, you did actually go to uni then? Yeah. Was a lot of people referred to a specific track that
Things Can Only Get Better.
Oh, that was you. That was
D-Ream.
Jesus. You're really, I mean, in many ways, the reason we're now stuck with a defunct Labour administration that is falling apart, it's all your fault.
The first term is my fault.
Yes.
So 97 to 2000 and whatever.
Yeah, which wasn't that bad.
No, all the great things, increased investment in health service,
things only got better.
In education, all absolutely fantastic.
Yeah.
From the second term onwards, it's nothing to do with the old.
Nothing to do with you at all.
So I take full credit for the first term of the Blair government.
Yeah.
And then 2001 onwards, everybody else's problem.
Right. Well, in a similar way, you've had that experience of sort of showbiz and then sort of proper work that's useful to the world.
And now back again.
And I'm always interested in engineering and technology and things, but with absolutely no technical ability. I mean, I did rebuild cars. I got a certain amount of mechanical ability.
Yeah.
But as soon as it got to understanding effectively physics and anything to do with mathematics, and I was completely at sea.
I must say, I wasn't a natural mathematician. You meet some people who just can do it.
Yeah.
And I certainly wasn't at school. I didn't like it very much. I like physics, but maths I found difficult. And then when I was about 23, went to university and realised that it's practice. For most people, it's practice.
Yes.
So it's like sitting at piano and thinking, I'm going to play this. And then you go, well, I can't. And just stop. You know?
Yeah.
And actually, maths is like that. It's like playing an instrument. The more you practice, the better you get it.
Yeah, no, I'm sure you're right.
You never, you're not going to be a prodigy. There's some people who just appear to be able to do it. Very few. Same with instruments, I suppose.
Yes.
Most of us have to learn how to play an instrument, and you have to learn how to do maths.
There's also there's a lovely theory I read earlier this year about 10,000 hours, which is I don't know if you heard of, I can't remember the book now. There's a guy that worked out that the people who are brilliant at something, they're not. They've just done 10,000 hours practice.
It's probably,
And and he uses Bill Gates as an example. Bill Gates was suddenly like 22 and a maths and a computer programming genius. No, he wasn't. He was given a computer when he was 9, and there was only 2 kids in the world that had computer access at that age.
Yeah.
And he had 10,000 hours of practice before he became well known and he did something with it. It kind of lets a lot of people off the hook when you go, I've never had any practice and that's why I'm rubbish at everything that I've ever done. Yeah.
I don't know if it's comforting or not. It's like when people say, well, I'm really bad at something, it's like, because you're a lazy bastard.
Yeah.
That's what it actually says, isn't it?
I think
you're bad at this because you're a lazy bastard.
I think we have to accept that. Some people are, everyone has potential, but some people have very little and they're lazy. And we have to accept that. I have to accept that as a wet liberal where I think everyone deserves the same, all that stuff. But I've met some people who are thick and quite dull. And, I've tried to love them and it's very hard and you have to make that extra effort. But they really are pretty bloody useless.
But the new theory says that's because they haven't spent 10,000 hours not being stupid. So it is their fault, isn't it?
It is their fault.
You've just spent 10,000 hours not being stupid.
You'd be less stupid. I want to blame them. That's the main thing. I want to carry on blaming them. It is their fault still. Good, that's good. But have a quick look at your questions. I mean, there's some very funny ones. But there's ones about your baby as well, which is very lovely.
I'll be back up in
Are we getting straight with the new baby in the house?
Yeah. He wakes up, he goes to sleep at about, I suppose, after news night.
Right. Oh, really? I see. He stays up that late. Disgraceful.
Well, he just sleeps around. But I mean, he wakes up every 4 hours to be fed. Right. So if he goes to sleep at midnight, then he wakes up at 4, and then he wakes up at 8.
Yeah.
So it's not bad.
Because how old is he now? He's very few days.
A week. A bit. What day is it? Is it a 9-day?
Yeah. 9 days old. He's very gorgeous.
Yeah.
And his little toes did a little bit of wriggling just now when he did a poo when I saw him, which is very encouraging.
Next great fuel source, nuclear fusion.
Right. You think
obviously.
Yes? And if we get rid of all, what will replace it? Oh, I see that one. Okay.
It's got to be fusion eventually.
Yeah.
I mean, I don't think anyone disagrees with that. We've had it if we don't work out. Although you can power the world with solar power if you want. There's enough solar energy.
Yeah.
There's the magic number is about. Well, it's 1.3 kilowatts per metre squared at the top of the atmosphere. So, and it's about 200 watts, I think, what you take, between 100 and 200 watts at the surface, depending on where you are, the equator or further up. So you can get about, let's say, 100 watts per square metre.
And is this photovoltaic cells?
Yeah.
Right.
So they work, and you can do that, and that's enough. You can power. I think the world energy consumption is, what is it? I have read this. 10 terawatts, 12 terawatts, something like that.
Yeah.
So you can do it. The problem though is So you could do it in the Sahara Desert.
Yeah.
The problem is
Is then
storing
moving it, or
So-
storing
so-
it and moving it.
So you probably need to make hydrogen or something, and then. But that's what
Right.
you do with fusion anyway. There's 3.5 billion. The
Right.
science budget.
Right, for the whole thing.
0.25% of GDP.
Right, yeah.
Idiotically small.
Yes.
Right. So if you ask the question, what would happen if you doubled it? Britain would be world leading. It'd be the #1 place to do science in the world. So this is an extra 3.5 billion a year, right? Which
Right.
is, it's just, I don't understand why we spend so little on science and technology.
Yeah.
So you ask, how could we get fusion power stations working? How could we develop better batteries for cars like this? How could the answer is you pay for it.
Yes.
And it's really cheap.
Yeah.
Actually.
Yeah.
And
Well, and that's particularly the long-term effects are so hugely beneficial for everyone. I mean, it's just
the government figures are that 6.4% of UK GDP comes from physics-based industry, just physics. 6.4%, more than the City of London, which was 4.9. It's probably like 3 now.
Yes, or minus something.
So
yeah.
6.4,
Wow.
we spend on all of science, including medical, 0.25% GDP.
Right.
So the answer is when all these brilliant things happen, when we decide to
And
fund
we
them.
actually fund them and get them.
Yeah.
No good. We'll have a good rant about
Bit of
it.
that.
Yeah.
Is the LHC going to cause the Earth to fold in on itself? Nope.
I love that. Well, there were so many Twitters about that at the time you were first running the experiment. So many people went, bye bye world, it's all going to fold into a... But then the other one was, it's already happened and we don't know it. We've gone into another reality. I like that one. So.
I love the idea that so you say that, so the particle physicists, right, all the scientists say, no, that's not going to happen.
Yeah.
Right? And then, well, you would say that. Like, well,
Yeah.
my opinion, it's like, well, hang on a minute. You're not allowed to have an opinion
Yes.
unless you know
Yeah.
something
about what
just
you're talking
tiny,
about.
Yeah. Well, you can have your opinion, but you don't have a right for it to be listened to.
Yeah.
I mean, you do need some knowledge. I mean, the example I like to use is a plane. If you say, you don't sit on a plane and go, well, I think the wings, I don't want the wings to be like that.
Yeah.
I reckon
They should be
they should
square.
be like that. Right, I reckon.
I want them to look like a Lego aeroplane.
You don't know, but hang on. You need a bit of aerodynamics training to design a plane wing.
Yeah.
But no. But it's the same with the LHC. It's like,
Yeah.
do you think it's silly? There's some great questions here. Given that everything was one at the moment of Big Bang, is there a case for pantheism?
I do like that. There's quite a lot of God questions.
Yeah.
Yes. Do you believe in any form of afterlife?
No.
Okay. That's that one
It's
answered.
just thermodynamics. I don't know. I can't get over it. I just can't get around thermodynamics.
Explain why. Because thermodynamics
right.
a good scientific reason as to why there isn't an afterlife.
Well, I think so. I mean, the thing is, you need, as far as I'm concerned, we're information processing devices.
Right.
So we're processing information at the moment.
Yeah.
Which requires energy. It requires actually temperature difference to do
Yes.
that. And so we generate that by eating food, convert it into energy, and then there's some temperature differences
Right.
around so we can do work.
Right.
So we're a heat engine. That's what we are,
Right.
heat engines. And so if you stop providing the power source, then you stop processing information.
Yes.
And
then you stop.
I can't get beyond that.
Right. That
I mean,
sounds very,
therefore,
very convincing.
Steam engines work, and fridges work.
Yes.
Fridges work by taking heat out of the box by having a big
outside.
heater on the back of them.
Yeah.
If you ever wonder why a fridge has got a heater on the back of it,
Yes.
which seems a weird thing to do, but the temperature of the back of the fridge has got to be higher than the temperature of the kitchen
Yeah.
in order to allow it to do work and take the
Right.
heat out of the fridge. And
Right.
that's how it works.
Yeah.
And that's how we work as well.
Yeah.
So if there were an afterlife, I would have to reconsider the engineering design of fridges with a very critical eye, and I have to get really worried and think that I don't understand the universe.
I mean, there's certainly a great story to be written of the physicist who wakes up and he is in heaven.
It's like, well, how do
He's going, well,
fridges
hang on a minute. How do fridges work then?
Yeah, that's the first thing I'd say. Does Brian think string theory will unite quantum mechanics and relativity?
Wow, I remember reading that one and going, I don't even know what that means.
Well, quantum mechanics and relativity. So quantum mechanics is a theory of the small, right, atoms, molecules, quarks, subatomic
Right.
particles. That's quantum mechanics. And three of the four forces of nature quantum theories, right? Which basically means quantum means discrete, or so it means that
right.
So, for example, an atom's got a nucleus with electrons essentially in orbits in particular places around the atom, and so they're actually energy levels. So if you heat sodium up, it glows orange because, or yellow, because the electrons jump from one bit to the other and then back again. So they can only be here or here, and somewhere in between. So that's what quantized means, or quantum.
Right.
So 3 of the 4 forces of nature are quantum theories. The one that isn't is gravity.
Right.
Einstein's theory is the best that we've got. So
I'm just going to go around the block once more while you're doing this.
So string theory is an attempt to build a quantum theory of gravity. That's what it is, right? Basically.
Right.
And we don't know whether it works yet.
I'm not saying right because I understand. I'm saying right because I'm trying to understand.
So we'd like a quantum theory of gravity, because then we have a quantum theory of everything. And at the moment we've got a quantum theory of almost everything, and not of gravity.
But gravity.
So gravity, the best theory we have, 1915, Einstein's general theory of relativity, and it's not changed since then because it's beautifully accurate. It does its job.
But why the word? Because it's the string bit that throws me. Because I just think of string that you tie up a parcel with, and that's sort of too literate.
Basically, the problem with gravity. Your gravity.
Yeah.
You're coming.
It's always been a problem for me, your gravity. I've never been easy with it.
The problem roughly boils down to the fact that you've got these particles look like points in that theory, in Einstein's theory, basically.
Right.
And what string theory does is make them little loops of string, basically.
Right.
So because they're not point-like, you get around some of the problems, basically. So it's kind of a way of trying to solve the problems and build a theory that looks like a quantum theory of gravity. And no one knows whether it's right or not, because it's very difficult to test experimentally. Every measurement we've ever made of gravitation, and it's very difficult because it's so weak as a force, it's incredibly weak compared to all the others, have agreed with Einstein's theory. So you need to do some experiment that tells you where to go next.
He was a bloody clever bloke, wasn't he, that Einstein?
Amazing.
The more I've ever found out about him, I just go,
I'm going to give you my book. I'll give you a copy of my book, which is out in July.
Oh wow!
It's called Y = MC squared.
Oh wow! And might I understand it?
Yeah, the idea is that we derive. I say we because it's a friend of mine, Jeff Forshaw, is a theoretical physicist at Manchester, and we've written a book because Gia, my wife, asked Y = MC squared. I want to know energy and mass, right? All right, and I can understand that you change one into the other.
Yeah.
But c squared, speed of light.
Yes.
Squared. Why is that the exchange rate? What has the speed of light got to do with energy and mass?
Yes. What a brilliant question.
So we derive E = MC squared. Actually, we're using only Pythagoras. As long as you can do Pythagoras, you should be able to. If I drive my car at speed of light and turn my headlights on, what will happen? Read my book. I'll tell you what the answer is, though. I'll lose the sale. The answer is that the light will disappear away from you. Well, actually, there's a subtlety here.
It's quite a clever question, that one. I did get that one.
If you travel at the speed of light, you have to be massless for a start.
Yes, because otherwise you'd weigh 1,000,000 trillion tons, wouldn't you?
Oh yeah, but interestingly, only if you're massless, not only can you travel at the speed of light, you have to. So you're forced. You can go in there.
Yeah.
So the structure of space and time, as sort of elucidated by Einstein, forces you to go at the speed of light if you've got no mass. So you go at the speed of light, and no time passes for you at all.
Right.
No time passes. All your speed, as it were, through space and time is used up flying through time.
Wow.
Flying through space at the speed of light, so no time passes. So the answer is that you can't travel at the speed of light and then turn your headlights on, because no time passes for you at all. So there's no sequence of events that are possible, so you can't do it.
Well, the viewers of Carpool are frighteningly scientific people and ask really complicated questions that are completely beyond me to answer. They're all cleverer than what I am. So So do we...
Okay,
now,
so put it wherever you want. You can put it in your pocket. It's got a smart
kidding.
key system.
So what do you do then?
Throw
You
it right there. Press,
do
put your
I
foot on the
foot on
brake.
brake?
Press the power button.
Press
There
the
you
power
go. And
Oh, look at that! This is completely different design then, isn't it? Look at that.
absolutely, yeah. So all the functions you used to on the screen is right here. A lot of them we've moved up there, and this is just for the navigation now.
Wow. Look at that. Oh, I have to say, I've used a lot of sat-navs. You know, the ones you put on your dash and on your phone and everything. The one in my original Prius is way the best.
Good.
It is really good. It doesn't get me lost. She's polite. She doesn't get cross.
That's nice.
When I go the wrong way,
with you.
she doesn't get upset with me. Now, I've got the foot brake
You can
off.
also do this, though. I know you don't have this on your Prius. Yeah, I know you wanted that.
I want that.